Today is a review session. What do you want to talk about? Michael.
Supernodes.
Supernodes. All right. You have a problem in particular? Or would you like me to just make one up? Make one up. Okay. I will make up a problem then. Do you want a dependent source in it or no? All right, so this is a problem that I have just made up, so I have no idea what any of the answers are, but we'll be okay. This problem will illustrate the nodal analysis procedure, including supernodes, okay? So because we are going to work this problem specifically with nodal analysis, the first thing that we have to do is identify our nodes and then assign a reference. So here's 1, 2, 3, 4, 5. All of our nodes have been identified. I'm going to choose the bottom node as a reference node. So steps 1 and 2 are taken care of. Step 3 is always to write our controlling variables in terms of our nodal voltages. So how do I express Ix, the current flowing down? Oh, excuse me, I need to label my nodes. Let's call this A, B, C, D. So now I need to express my controlling variable in terms of my nodal voltages. So how do I express Ix in terms of my nodal voltages? All right, I agree with that. For every voltage source that I have, I will have a voltage relationship. So let's start with the 8-volt source on the left. How does that relate to my nodal voltages? All right. And for my 3Ix voltage source in the top middle, how does that relate to my nodal voltages? VB minus VC. Okay, so what I'm going to do now is I'm going to draw a circle around my supernodes, okay? So anytime I have a voltage source, I have a supernode. If the voltage source contains the reference node, like our supernode for the 8-volt source does, we do not write a Kirchhoff's current law equation for it. If the voltage source doesn't, or the supernode does not contain the reference node, we do write a KCL equation for it. So our KCL equation for supernode BC, KCL at is going to be adding this current that's leaving node B of the supernode, plus this current that's also leaving node B of the supernode, plus this current, which is leaving node C of the supernode, plus this current, which is leaving node C of the supernode, all added together and set to 0. So what's that going to look like? VB minus VA over 9 ohms, okay? All right. Okay. Okay. Is equal to 0. All right. One thing that we could potentially do here to simplify this significantly is to call this contribution right here 1 amp and not do KCL at node D, because it's obvious that 1 amp of current is flowing through that 10 ohm resistor, because that 10 ohm resistor is in series with the 1 amp source, which would give us a 3 equation, 3 unknown system. Actually, now it's down to 2 equations, since VA is obviously 8 volts, and then we can solve from there. So there are a couple of different tricks that we could do in here to reduce our number of nodes and make this a little easier to set up. But anyway, did that help explain? All right. And then at this point, it's just throw it in a calculator and go nuts, which I don't want to do. All right, what else can we talk about?
Can we do a superposition problem with a
Sure. So let's say that we have a 10 volt source, a 5 ohm resistor, two VX dependent source, a 4 ohm resistor, and a 3 amp source. And our voltage VX is this voltage, okay? And our ultimate goal here would be to try to determine the quantity VX, or the contribution of the 10 volt source to VX and the contribution of the 3 amp source to VX, okay? So with voltage source on and current source off, this is going to look like our 10 volt source in series with our 5 ohm resistor. Here we have our dependent current source, twice VX. Here's VX. Here is our 4 ohm resistor. And we turn our current source off by replacing it with an open circuit. And this is a little difficult because the current, so the voltage drop VX is going to be 5 ohms times the current flowing into the positive polarity terminal, which is negative 2 VX. So we have VX is equal to negative 10 VX, which means VX, or in this case, I guess it would be VX prime. That's B0. So the 10 volt source doesn't actually contribute anything, is what it appears. With the voltage source off and the current source on, Our 10-volt source would look like a short circuit. Here's our 5 ohm resistor, and let's call this Vx double prime. Here's our current of 2Vx double prime, our 4 ohm resistor, and our 3 amp source, if I'm not mistaken. And using Kirchhoff's current law, we can say that Vx double prime would be the current flowing into the negative polarity terminal times the 5 ohm resistor. So that's going to be 3 amps flows in plus twice Vx double prime. And then we need a negative sign out here. So let's see. So Vx double prime is going to look like negative 15 volts minus 10 Vx double prime. So 11 Vx double prime is equal to negative 15 volts. Vx double prime is equal to negative 15 over 11 volts. And that's the contribution of the current source to the quantity Vx double prime. So effectively, if you're using superposition and there is a dependent source, you just have to leave the dependent source on always. You cannot turn it off, because the superposition theorem tells us that we can analyze circuits by leaving one independent source on at a time, but does not mention the ability to turn off dependent sources. Amps over volts, because it's outputting current and it's taking in voltage, so it has to be amps per volt. So that is an implied unit of 2 amps per volt for that coefficient there. All right, so winter 2019. Number 35. All right, so number 35, the correct expression that defines Vx in terms of the mesh currents, which means we need to scroll up to this horrifying picture. Let's make it a little smaller so that we can see it. All right. So how I would approach this and how I came up with the answer that's available on the test is I said that Vx is going to be the voltage drop over the 4 ohm resistor with this polarity plus the voltage drop over the 38 ohm resistor with this polarity from Kirchhoff's voltage law around this loop. So that would tell me that Vx is going to be 4 ohms, mesh current labeled I4, plus 38 ohms times the mesh current labeled Kevin, did you have your hand up a moment ago?
Yes, for fall 2020.
All right, so the energy absorbed by a circuit element is shown in the graph below. The power absorbed at time 3.189 milliseconds is closest to ... Okay, so power is equal to the derivative. So at 3.189 milliseconds, what I'm going to do is I'm just going to put this guy right here. Well, this slope is the power. So I just take the slope of that portion of the graph and I'm good to go. So we see a change. So it changes from, let's see, or actually it's the change in y over the x, right? So y2 minus y1 over x2 minus x1. Y2 in this case is 0 kilojoules minus 10 kilojoules over 4 milliseconds minus 3 milliseconds. Looks like negative 10 kilojoules per 1 millisecond. So 10 times 10 to the 3 times another 10 to the 3 would be 10 megawatts, negative 10 megawatts. Yep. Thing. We could do that for an entire day actually, but let's. Let's see. So you said 12 and 13, right? Okay, so let's look at number 12 here. So if these resistors have these particular values, find the value of Vs. Okay, so I would argue that this is we can definitely apply the properties of voltage division to this problem, but we're actually going to apply them backwards, okay? And so what I mean by that is that 0.1 milliamps times R2, which is this voltage drop, let's just call it Vx for the sake of argument, has to be equal to Vs times R2 times R3 over R2 plus R3 divided by R1 plus R2 R3 over R2 plus R3. And then we would solve for Vs. So that would be a way to do it using voltage division, effectively voltage division backwards. Another way to approach that is you can figure out Vx by simply taking 0.1 milliamps times R2, divide that Vx quantity by R3, and you get the current flowing through resistor R3. Apply Kirchhoff's current law at this node, and you get the current flowing through R1. You can then determine the voltage drop across R1, and then the voltage drop across R1 plus Vx gives you Vs. That's an alternative way to do it in several easily digestible steps, but Colby's suggestion of using voltage division to get it done in one is absolutely valid. You said 13 as well? Okay, so 13, we have a potential current division problem. So how you could approach this using current division would be first to combine those two current sources in parallel. So 25 milliamps up in parallel with 15 milliamps down looks like this 10 milliamps up. The current flowing through that right-hand branch is going to be 10 milliamps times 1 over R2 plus R3 divided by 1 over R1 plus 1 over R2 plus R3. So that gives us the current flowing in the right-hand branch. If we multiply that whole thing by a factor of R2, that gives us our voltage V2. That's a combination of current division and Ohm's law to get the answer in a single equation. You could do a source transformation and then use voltage division. Absolutely correct. So what that would look like would be V2 is equal to 10 milliamps times R1, which is giving us our voltage source. And then we're going to multiply that by the ratio of R2 over R1 plus R2 plus. So that's doing a source transformation on the practical current source formed by the 10 milliamp source in parallel with R1, and then applying voltage division to that relationship or to the resultant circuit, because it's then just a voltage source in series with 3 resistors, and you just want the voltage drop over the resistor R2. So that's an absolutely great way to think about it that I don't know that I thought of before. So good job. Devarier.
So this is the question about this problem. What if we got like a current flowing and then middle node R1 and 15?
So something like this, how would we find that current?
How would you like include everything?
Okay, so so you're suggesting here, if we had a current source there, let's call it 5 milliamps, like so. Erase this other stuff because that changes things significantly, actually. So what it changes specifically is that our current, so our 25 milliamp current source and our 15 milliamp current source are no longer in parallel. So we can't actually combine any of the current sources because there are no current sources in parallel. However, what it would allow us to do is to apply Kirchhoff's current law. And so by that, I mean, this current flowing down is obviously 25 minus 5 or 20 milliamps. This current flowing to the right would be 5 minus 15 is negative 10 milliamps. And then we would know the current flowing through resistor R2, and then thus the voltage drop. So that would change it from a current division problem to a KCL problem. Or you could, in my opinion, vastly complicate the problem and use mesh. Fall 2019. Thing keeps trying to trick me into putting Windows 11 on it. I will not fall for it. I'm sorry, I forgot what problem. 15? All right, so we're trying to find the resistance between C and D. Okay, so I'm going to label my nodes. How many green? All right, so A, B, C, and D are all taken. So let's call this guy E. This guy up here is still C. This guy here is still D. Let's call this guy F. This guy G. This one is obviously A. This one is B. This one is C. Okay. So we're looking for the resistance between C and D. So I'm going to put C over here and D over here. And there is one direct path, right? To go from C to D directly is just the 18 ohm resistor. Yeah, so I look for a direct path first, and then I look for a different path, and I explore the different ways that I could go for that different path, right? So what I mean by that is I'm trying to go from C to D, right? So the 18 ohm resistor is the most direct path. Probably the next easiest path would be to go from C to F to D. So I'll do that one next. So C to F is through resistor R. From F to D is through the 9 ohm resistor. So that takes care of this guy and this guy. And then the last way that I can do it is to go from C to B to G to F and then to D. So from C to B is the 8 ohm resistor. From B to G is the 6 ohm resistor. And then from G to F is another resistor R. And that's it, okay? Now I say that's it, even though there are these 3 resistors here up top, because they're all shorted out by that short circuit. So effectively, including any of those resistors, the resistor R between nodes A and C, the resistor, the 20 ohm resistor between A and E, and the 14 ohm resistor between E and C only show up in a path that goes from C to C, which means they shouldn't contribute anything to going from C to D because they're shorted out. So I would have 8 in series with 6 in series with R, that combination in parallel with R, that combination in series with 9, and then that combination in parallel with 18, and ostensibly the answer is then 14.361 ohms if I did it correctly, which I'm going to argue I probably did. It's not guaranteed for sure. I definitely make mistakes, but
You're to draw those 3 short resistors on this.
so they go from C to C. So effectively, I'd put them something like this, because they connect back to the same node. Yeah. $18 from this test. Right, so what are we doing here? Trying to find the current IX. Okay, so here's another place where I'm going to do current division, but I'm going to do current division twice, okay? So, no, I'm not. I'm just going to do current division once. Sorry. So IX I'm going to have my 6 amp source. Then the branch I want has a resistance of R1 in series with R2 in parallel with R3. And because I'm pressed for space, I'm just going to write R2 in parallel with R3 like that and assume you guys know it's R2 times R3 over R2 plus R3 divided by 1 over R4 plus 1 over R1 in series with R2 in parallel with R3. And because our current source is pointed down, that's opposite the direction that I would expect here. And so I'm going to put a negative sign up. For part 19, or problem 19, the power absorbed by resistor R3, once I know what that current IX is, I can then apply current division again to get just the current flowing through that particular resistor. And then the current squared times the resistor value gives me the power. You would not, because you're just saying, I know how much current flows into this node, and there are 2 parallel paths. Yeah. So you would not need to take into account R4 at all in your second current division equation. So current division can only be used for resistors that are in parallel. So effectively what I'm doing is I'm treating this as a single resistance that's in parallel with R4. Voltage division can only be used when resistors are in series. So in that previous example, I had to force resistors to be in series by getting an equivalent parallel resistance, and then I just put that equivalent parallel resistance in as one of my series resistors. So similar, but opposite to what I'm doing here. Colby, I believe you had your hand up. All 2020, problem 20. Okay, let's see what we have here. All right, so the first thing that I would do would be to take this guy and replace it with a practical current source. Okay, so that would then put, let me work this one all the way out, because describing it in the space that I have here is not going to be particularly great. So let's see. So 11, 18, and 2. $11, 14, and 7. Okay. $11. I think. And then the VL, okay, so everything to the right of that actually doesn't even matter. So I'm trying to make this thing look like a practical current source, right? Okay. So as I mentioned a moment ago, the first thing that I would do would be to take the practical voltage source on the left-hand side and convert it into a practical current source. So here's my 2 amp source. My 11 ohm resistor, my 14 ohm resistor, 7 volt source. All these are staying the same. Then I'm going to have an 18 ohm resistor here, and then a current source direction up. That is 11 over 18 amps, right? Now I have 2 current sources that are in parallel. So what I'm going to do is I'm going to combine those 2 together. So 11 over 18 plus 2. Looks like 47 over 18. So I have 47 over 18 just in parallel with 18 now. Here I would convert that practical current source into a practical voltage source. So that would give me 47 volts in series with an 18 ohm resistor. I could combine the 18 ohm resistor and the 11 ohm resistor because they are in series. So that's going to be 18 plus 11 is 29. And now what I'm going to do is I'm going to convert both of these practical voltage sources into practical current sources. So 47 over 29 amps in parallel with 29 ohms. And then I'm going to have 7 over 14. That's going to look like half an amp in parallel with 14 ohms. And my 47 over 29 is in parallel with my 1/2. So 47 over 29 plus 1/2 looks like 123 over 58 amps in parallel with 29 in parallel with 14. $406 over 43 ohms connected to my load resistor, which I can't change. So 123 over 58 is the value of my current source in my practical source representation. And for maximum power transfer to occur, the resistor RL has to be exactly equal to 406 over 43. I feel like whenever I put things like this in circuits, it tends to trip you guys up, because there were a lot of questions about how to handle that on the in-class assignment that had that configuration as well. So notice what I did here. I just took that part out. So I created a terminal here and here, which is this guy here, here. Took that practical voltage source out and then replaced it at those terminals with the practical current source, then I observed that that places the 1/2 amp current source in parallel with our normal looking current source on the left-hand side. Similarly, the 14 ohm resistor gets placed in parallel with the 29 ohms. So I explicitly set up terminal pairs, disconnect the practical source that I'm transforming, connect back to that same set of terminal pairs, the revised or the electrically equivalent practical source, and then go to my simplifications. If you don't get into that mindset where you're looking specifically at your terminal pairs, taking something out and putting something back in, it's very easy to make a simple mistake. Yes, so the last 3 pages of the exam are completely blank. You can tear them off, just turn them in if you write on them. Yeah. So the power absorbed by the load resistance if RL is equal to 5 ohms, okay? So that means that we would have the 5 ohm resistor right there. So I'm going to call this current IL. Using current division, IL is equal to 123 over 58 amps times 1 over 5 ohms divided by 1 over 5 ohms plus 1 over 406 over 43 ohms. And then the power is just IL squared times 5 ohms. Where I chose to do it that way to illustrate yet again current division. I could have done Ohm's law, so I could have said 123 over 58 times 406 over 43 in parallel with 5, which would have given me my voltage drop. And then the voltage drop squared divided by 5 ohms would give me the same answer. But it said power, because maximum power, let's look at it real quick. The power absorbed by the load resistance RL, if RL is 5 ohms. Well, 5 ohms isn't when maximum power transfer is going to occur, because that isn't the value of the resistance in parallel with the practical, excuse me, with the ideal current source, or the resistance of the practical current source, I guess would be a better way to put it.
Why was the current division not 1 over?
I hope you misread it, because it was, yeah, it is 1 over those numbers.
Oh, okay.
Yeah. Oh. 18 and 19. All right, let's see here. So we're trying to find the voltage Vx. So what I'm going to do is I'm going to write a KVL equation around this path, where I'm following the current, which is 3 milliamps. And I know that all my voltage drops across my resistors are going to be 3 milliamps times the resistor value, because a current of 3 milliamps is flowing in the outer loop, right? So what I mean by that specifically is that the voltage drop over this 10 kilo ohm resistor has to be 30 volts, because 3 milliamps times 10 kilo ohms is 30 volts. The voltage drop over this 1 kilo ohm resistor has to be 3 volts with this polarity. And the voltage drop over this 3 kilo ohm resistor has to be 3 times 3 is 9 volts. So from that, I would have negative 15 volts plus 30 volts plus Vx plus 3 volts plus 9 volts is equal to 0. So Vx would be 30 plus 3 plus 9, so that's 42. Hold on, negative 42 plus 15 volts is equal to negative 27. No, so, and this goes back to the in-class assignment again, where I specifically introduced problems that did not have a closed loop, okay? So for a Kirchhoff's voltage law loop, I would prefer to call it a path because loop does imply that there are things closed, okay? Kirchhoff's voltage law is simply the sum of voltage drops. You do not have to have a current, right? So like if you take this Vx right here is effectively asking you what you would see if you connected a multimeter between this point in the circuit and this point in the circuit, which does not have to have a conducting path. It's simply the potential difference between those 2 points, okay? So whenever I'm taking my voltage drops over resistors, they have to have a current flowing through it. If it doesn't, the voltage drop is 0. So this is just the voltage drop over an open circuit, right? So it can have any value that it needs to have. The power supplied by the current source. So once I know what Vx is, then I could call this guy V current source. KVL around the outside loop to get the voltage drop over the current source. Voltage drop over the current source times 3 milliamps gives us the power absorbed. We want supplied, so we want current flowing into the negative polarity terminal. So I would actually write the polarity of it like that to make solving for it. So this kind of goes back to, let me see if it was problem 35 on this test maybe. Yeah, what we did here. This is a voltage drop. The Vx that we were trying to find was the voltage drop just between 2 points in the circuit with no current carrying path. And we just did KVL around things that carried current to figure out what was going on. The exact same principle we applied in that last problem. Too far. All right. So number 9, we have a charge of 34.548 amp hours. 34.548, excuse me. Amp hours. So let's see. 1 ampere is 1 coulomb per second, right? And then 1 hour, 3,600 seconds. So let's see. So the amps cancel this, hours cancel this, and then per second cancel second. So that gives me an answer in coulombs. And then if I want kilocoulombs, 1,000 coulombs per kilocoulomb. Coulomb cancels coulomb. There we go. Multiply those numbers out. That's number 9, just playing with units. Number 10 here, the lightning bolt can carry a very large current that lasts for 148.143 microseconds. If it delivers a very large amount of energy, the charge accumulated on the chassis. Okay, so charge, Q, is current times time, right? Because current is charge over time. So multiply this number by this number, and you're good to go. This is there because I'm a jerk and gave you extemporaneous information. If it makes you feel any better, I distinctly remember Dr. Cronk getting on to me for doing that, and I said, I don't care, I'm still going to do it. That's correct, 25 questions. 5 of which are theory questions like these first 10. You could argue number 9 and number 10 aren't really theory questions, but they're very short calculation questions involving understanding units. So to me, that constitutes a theory question because this is of the level of difficulty you saw in your engineering 120 exams. And then problem 6 through 25 will be circuit analysis questions more in line with what you see here, 11 through 35. They are all exactly the same. Everything is worth 4 points because 4 times 25 is 100, right? Yeah. Yeah, I might have screwed something up. Always a possibility. And especially on the easy ones, I screw things up a lot. Power absorbed. So P here should be I times V because the current is flowing into the positive polarity terminal. It should be V squared over R. And it should be I squared times R. Those are the 3 actually correct answers. So I times V isn't on here. V squared over R, so that's this guy. I squared times R is this guy. So D is actually wrong. That doesn't make any sense. So that's my fault for screwing that up. I would gonna blame errors, copying and pasting crap. So yeah, this one is decidedly not right. Thank you. So since it's obvious that I screw things up from time to time, let's talk about what that means if it happens to you on your exam tonight, which I sincerely hope it doesn't because I understand that it is a pain in the ass for you all, and it is also a pain in the ass for me. So if there's a problem on the exam where, so let me put this, J, none of the above answers are correct, should actually never be the correct answer on any of my exams. It is there specifically as a save my ass type thing. That being said, what I traditionally do is if the correct answer isn't actually available, And I can usually tell this by, I do a statistical analysis of all of the problems and see how many people got the correct response. If it's less than 30%, I check to make sure that the correct answer was available. Sometimes the correct answer is available and people are just really bad at that problem and that problem stands. You should just be better at that because I am a jerk. If the correct answer was actually not available, everyone gets credit for that problem. So that's how I handle when I screw something up. If I was right, then it seemed like a reasonable test question to me and you were actually graded on it. If I was wrong, that was unfair of me and everybody gets credit for that problem. So if you've worked a problem, let's say 2 to 3 times and you're not seeing the answer, it's quite likely that I've made a mistake. It's either I've made a mistake or you don't know what you're doing. One of those two. It's a pretty binary decision. Yes.
This one, if it was asking for power supply, it would be the same, except it would be P equals negative I.
That is correct. Mm-hmm. All right. Contribution of the 4 amp source. All right, I think this is going to involve me having to actually recopy the problem. Okay. Number 24. All right. Okay. Number 24. All right, so I'm trying to decide if I should use nodal analysis or mesh analysis. There are obviously 4 meshes here. Regarding nodes, I see 1, 2, 3, 4 nodes, but one of them is going to be ground, so it looks like nodal analysis is going to be the way to go. I'm going to identify that's 1. That's 2. Actually, I should have drawn this one better. The one that you probably are missing is this guy right here between the 7 ohm resistor and the 8 volt source. And this guy down here. So I would choose the bottom node to be my reference node. So let's call this VA, which makes this guy also VA. This is VB. And this guy is VC. So we do have a dependent source. So we have some controlling variables. So our controlling variable IY is VA minus VB over 4 ohms. Vx isn't really a controlling variable here, but I'm just going to go ahead and write that equation. Vx is negative VA. I have a voltage source, so I'm going to have a voltage relationship. So VC is equal to 8 volts. I don't have any supernodes that don't contain ground, so now I'm just going to write KCL at node A and KCL at node B, and I'm done. So KCL at A is going to look like VA minus 8 volts over 7 ohms plus VA over 3 ohms plus VA minus VB over 4 ohms is equal to 0. So that's this guy, and this guy. KCL at B. I'm going to have this guy, this guy, this guy, and this guy. So that's -2 amps plus 1.5 IY plus VB over 6 plus VB minus VA over 4 is equal to 0. And I did, absolutely I did. Thank you for that. Plus 2 amps. Thank you for that correction. 100% did. Thank you very much for that, Dylan. Yeah. All right, so now I have enough equations to solve, so I would solve. At this point, it's calculated time. The positive polarity terminal is at 0. Negative polarity terminal is at VA. 0 minus VA is negative VA.